Hello everyone, welcome back to Operating System series. In the previous videos, we have learned FCFS, SJF, SRTF and priority scheduling. Today in this video, we are going to learn how another very important scheduling algorithm which is called as round robin scheduling would work, which is commonly known as RR scheduling also here. Round robin scheduling is one of the most widely used scheduling algorithms in, I can tell, in the modern operating system, especially with respect to the time sharing systems that we have. So this is what round robin is about. We'll understand the concept of round robin, everything. Now, simple thing how exactly round robin works. We have used different scheduling algorithms till now, which we have seen working, like FCFS, priority, all those things. What happens there is one process at a time works, and it will work until the completion, or if it is schedule the SRTF, then we preempt it. Here, instead of allowing one process to execute until completion, what we can do is every process gets fixed amount of time, which we call it as either time quantum or time slice. This time quantum or time slice, which we term it as a fixed amount of time given to each and every process. Suppose an example here, we tell that the time quantum, I'll just write it as TQ, time quantum is 3 milliseconds. Then what happens here? The CPU executes each process for the maximum of 3 milliseconds only. Either it can use lesser time slice or lesser time for execution, or maximum of 3 milliseconds. Once this time 3 milliseconds, whatever is allotted, it might be 3, 4, whatever. For this example, I'm taking as 3. This completes, the process has to come out for the ready queue. Again, it should come to the ready queue and it should reschedule itself. So this is called as round robin scheduling algorithm. Because the CPU keeps on rotating among all the process, we can term this as the round robin. And here it is clear that it is giving a fair CPU allocation to each and every process. And if you see, round robin uses a circular queue algorithm, which I told as which is suitable for the time sharing systems that we have. So based on this round robin scheduling algorithm, what we will do is, now let's solve a numerical problem. So here, if you see, we have 4 processes, P1, P2, P3 and P4, and all of them have different time slice requirement, like 8 milliseconds, 5 milliseconds, 2 milliseconds and 6 milliseconds respectively. And here we also assume that all of them came at the same time, that is 0th millisecond. But here only this much of input doesn't help. As we tell, this is a round robin scheduling algorithm. We also require something called as a time slice or time quantum, which is, with respect to this problem, is 3 milliseconds. So now what we will do is, you people already know, what might be the first step here. First step is simple, wherein we will be writing the Gantt chart with respect to 3 milliseconds, considering 3 milliseconds in mind. So first step, you people know, that is Gantt chart that I'll be writing for all the 4 process. So we'll start here. Anyhow, all of them arrived at the same time, 0th millisecond. I would be taking P1. It is requiring 8, but the time slice at once is only 3 milliseconds. So I can only run it for 3 milliseconds, and now 5 is remaining. This is 3. Then I have P2. P2 again, I'll subtract 3 and the remaining time is 2. This becomes 6. Now here, if you see, P3 requires only 2. As I earlier told, it can be 3 millisecond maximum or lesser than that. So I can just take P3 till 8 milliseconds And next comes P4. P4, 6 is there, so 6 minus 3, 3 is remaining. P4, this becomes 11. So if you see now, one round of chance for all the 4 processes is done, given. Now, circular queue will go to the second round. Again, I'll take P1. 5 is there, so 5 minus 3, 2 remains. So this is 11, 12, 13 and 14. Next, P2 is only remaining with 2. I can run till completion. This becomes 15, 16, 14, 15 and 16. P3 is already completed, not required. Then I have P4 with remaining 3. So it is 16. So it becomes 17, 18, 19. And last I have, now 2 rounds are over. Now I am coming to the third round. So what happens here? I'll again take P1, which is remaining with only 2 milliseconds. So it becomes 19, becomes 20, 21. So the Gantt chart is over. If you see, P1 has occurred 3 times. P2 has occurred twice. And P3, if you see, only once. Last one is P4, which has occurred twice. So we have all the process, completed the execution, considering 3 milliseconds as a time slice or time quantum. So this is done. Now, let's go to the second step. You people know what is the second step. Second step is calculating the average waiting time. Correct. Calculating the average waiting time. So here, we will do one process at a time. I'll take P1. P1 has multiple occurrence. So what I will do is, let me just consider the first occurrence 0 plus second occurrence and minus the ending time of first occurrence 11 minus 3. This has 3 occurrence, so I'll go one more time. Second occurrence, third occurrence, ending time minus third occurrence, starting time minus second occurrence, ending time. That is 19 minus 14. Yeah, it's 14, correct. So here this becomes 0 plus 8 plus 5. So it is 13 for P1. Then I have P2 considering. P2 is 3 plus 3 plus, this is the second one, 14 minus 6. So it is 3 plus 14 minus 6 is 8. This becomes 11. Then I have P3, which has occurred only once. So it is very simple. This becomes 6. Then I have P4, which has occurred twice. So it is 8 plus 16 minus 11. So this is 8 plus 5, which is again 13. So if you see, average waiting time would be 13 plus 11 plus 6 plus 13 divided by 4. Now what is this 4? 4 is the total number of process that we have. So this becomes 13 plus 11 plus 6 plus 13, that is 43 divided by 4, which becomes 10.75 milliseconds as the average waiting time that we have. So simple thing, 10.75, I'll just mark it with 10.75 is done. Now, what is the next step? Last step and third step, it is average turnaround time. Now this is again quite simple. We'll not worry on this too much. I just want when did P1 complete 100% of execution. So P1 completed here, it is 21 milliseconds. Then where did P2 complete? P2 completed here, that is 16 milliseconds. Where did P3 complete? P3 now only one occurrence, it is 8 milliseconds. Then I have P4 multiple occurrence, so it is 19. If you see it, it is 21 plus 16 plus 8 plus 19 divided by 4. 21 plus 16 plus 8 plus 19 divided by 4. It becomes 16 milliseconds of turnaround time. So if you see here, we have calculated the waiting time as well as the turnaround time here. It's 10.75, 16, as well as the Gantt chart that we discussed. So here, the overall problem tells we are giving equal opportunity for each and every process. It is a fair bit of time that is given. And here, when we talk about time and all, main thing, why is this used? Because I can avoid either convoy effect or the starvation for each and every process. So this is the main reason that we have. So we drew the Gantt chart, we calculated the average waiting time, we calculated the average turnaround time, and also we understood why all these things are required. So this is with respect to what you call the round robin scheduling algorithm, people.